But before we go into the algorithm, we are going to look at the structure of any directed graph in terms of something which is slightly a meta structure, right? Okay. So let me say that I have a big directed graph G, right? And now we all understand what is a connected component. In fact, those connected components are called as strongly connected components because they are indeed strongly connected, right? Right. So we are interested in finding out strongly connected components, in particular the same type of data structure or same type of information we want to maintain. That is, to every vertex we want to give its strongly connected component number such that two vertices get the same number if they belong to the same strongly connected component, two vertices get a different number if they belong to two different strongly connected components, right. So this is what we want our algorithm to do, and this is where we are leading to. So let me say that for the sake of, just for visualization, somebody has given us all the strongly connected components of this graph. What does it mean? Somebody has labeled for us a number 1 for all the vertices belonging to the first strongly connected component. This 1 is just subject to permutation, but yeah, so let's say that I have this strongly connected component, and so on, right. So these are the vertices. Let's now think of this as a meta vertex, one single vertex, right. So now this I will call it as capital X1. The internal vertices are there, V1, V2 something. Then there is this X2, there is X3 and X4. Now are these vertices, are these meta components going to be like independent, they will not have edges, or do you expect that there will be edges in this between these? Or what I would want to say is, can there be an edge from a vertex inside this component X1 to another vertex inside this component X2? Can it happen? Yes, no? All of you say yes? Okay. So there can be edges in between these components. Now let us ask, okay, so there is an edge from a vertex inside this component X1 to another. Similarly, there can be edges like this, there can be edges like this, and when I say this, it's quite abstract because I am not saying which vertex. Some vertex here has an edge to some vertex here. So in fact, I could have even not gone inside, I would have said that some X1 has an edge to X2. That's all I can say at a meta level. Okay, so I will draw some kind of possible edges. You should tell me whether I am making some mistake. So if I have edges, I can have edges which are, okay, sorry. So I can have edges going from X2 to X4, but then I cannot have an edge coming from X4 to X2. Similarly, I could have had an edge from X4 to X2, but then I should delete the edge from X2 to X4, right? So what kind of a structure do you see on this meta graph? That is, I just now forget that there are internal vertices, I just draw this X1, X2, X3 and X4, and I ask, okay, I will draw an edge from Xi to Xj if there is some vertex in Xi who has an edge to some vertex in Xj. And then I actually don't draw the edge from inside, I just draw it from X1 to X2 and so on. Now what kind of a graph do you expect to see? So for example, let me do the following. Can we get such a graph? It should not have any cycles. In fact, not only pairwise loops are avoided or pairwise edges are avoided, it cannot have any directed cycle. Why? Because again I can combine all of this and put all of this together and call it a big connected component. Therefore, I cannot have any cycles. So if somebody gives me the connected components and then if I draw these edges, what kind of a graph do I see? DAG. You have seen that yesterday, right? Directed graphs which do not have cycles are DAGs, and you expect to see that this meta graph is a DAG, right? So now, although we have not discovered the structure of the connected components, what we know is that the connected components themselves form a DAG between themselves, right? that is there is an underlying DAG which is there between the connected components. Okay, so now we are interested in finding all the strongly connected components of this graph, or in fact now we want to label this. Nobody is going to give us this labeling. In fact, our interest was not in finding this DAG structure because that is already there, but our interest is in labeling these vertices as x1, x2, x3 and so on. Okay, so let's ask first, what do we know about DAGs? I mean, what are the properties that we know about directed acyclic graphs? Any properties that you know? So this is a valid DAG, right? Yeah, so what are the properties that you are aware of directed acyclic graphs? You have studied one property certainly yesterday. There is some node which has in degree 0, right? What is such a node called? There is at least one node which has in degree 0, which is called a source vertex, source node. What about vertices which will there always be vertices which have out degree 0? But you have to claim that it goes to an ancestor, because it doesn't suffice to go to some arbitrary. For example, if you call this as the extreme vertex, right, this vertex x as an extreme vertex, then it has an out edge, but it doesn't complete a cycle. But what you want to say is this vertex, and if it goes to somebody else, then it should have a cycle. That is what you want to claim. So I will say that how did you choose that vertex, right? That is the claim. So if I choose this x does have an out edge, right? So these are on the correct lines, except that, I mean, I could have again argued against this, saying that I would have stopped at x, right? Maybe I would have stopped at x. So again, this is a correct, I mean, the claim is correct that there is always an out degree vertex. I will leave it to you to figure out that there must always exist a vertex which is also a sink vertex in the graph. There is always a source vertex which you must have proved, right? You must have proved that there is a source vertex in the graph. Yeah, we would like to see what can we say about, so in fact this DAG, which is a DAG of the meta or a meta DAG, will also have a sink vertex, which will also called as a sink strongly connected component. Because remember that although we have not discovered this structure, we know that in mind that there must be such structure. This is not the correct structure, but this edge is missing. But in fact, whatever DAG you have, there must be a source strongly connected component and a sink strongly connected component. There must exist one such component which is labeled as a source and sink. Does everybody agree with that? Just by taking the analogy from the DAG to the meta DAG that we have constructed. Okay, so suppose I actually happen to know what is a sink strongly connected component. Suppose somebody tells me that this strongly connected component, or these vertices belong to the sink strongly connected component, and I happen to pick a vertex inside that and start my exploration, right? Then what vertices will you see? So let's say that in fact in this case x3 is a sink strongly connected component. There are, of course, in the graph there are multiple vertices which are inside this sink strongly connected component. If I pick up a vertex which is inside this sink strongly connected component and start my simple DFS in the old graph, right? In the whole graph that I had, because I don't know this metagraph, I know that there exists such a metagraph, but if I am lucky enough and I pick a vertex here, what is the component that I will explore before I pick up the next vertex? Remember that there is a big for loop which we have, and then we are trying to explore that, right? But when I have picked up one vertex, what are all the vertices that will get explored? Only the ones in x3, right? All the vertices in x3 will certainly get explored. Why? Because if you pick a vertex, let's say A here inside x3, all the vertices which are reachable will get explored by the DFS property. Will any vertex outside x3 get explored? No, because by definition this is a sink strongly connected component, and therefore there is no vertex which has an outgoing edge to any other vertex, right? Is this clear? So these are the observations that we have. So now can you use these observations to now say that we possibly can design an algorithm based on these observations to find the set of connected components, strongly connected components in a DAG. So it is non-trivial. We have made some observations about the DAG, about the directed graph in terms of a meta DAG, and then also said that if we are lucky enough and if we pick such a vertex, then we can actually start the exploration there, finish the exploration, and then what should one do? Remove this whole component and then again do the same. So now we have a recursive smaller problem, right? This is very good. So now what are our tasks that we have in terms of finding out the strongly connected components? Sync strongly connected component or a vertex that belongs to the sync strongly connected component, right? So is this clear? What is the motivation for this? We are interested in finding a vertex that belongs to a sync strongly connected component. We know that a sync strongly connected component exists. We know that therefore that it must have at least one vertex. We would like to find out such a vertex and start our exploration. Once we do our exploration, we delete all the vertices in that and then proceed in a smaller graph which is obtained, and then do the same thing. We give this the component number 1. There may be multiple sync strongly connected components, it does not matter which we choose, right. So now let us go back to our pre-visit, post-visit numbers. Can you make any statement about a vertex or what kind of a pre-visit number or a post-visit number should such a vertex get which belongs to a sync strongly connected component? Sorry? Difference is 1 between what? Okay, so his claim is that, so I will write your claim, okay. If a vertex belongs to a sync strongly connected component, then pre-visit of V is equal to post-visit minus 1. That is what you want to say? Actually, we want a statement which is the other way. That is, we want to make a statement that if pre-visit and post-visit or pre-visit looks like this, then it belongs to a sync strongly connected component, right? Because that is something that is going to help us to identify a vertex which belongs to a sync strongly connected component. Is the kind of statement we want to make clear? We already have pre-visit numbers, we have post-visit numbers for every vertex. If we can say some statement that if the vertex has, in fact if you reverse this, that is if the vertex has pre-visit number is equal to post-visit number minus 1, then it belongs to a sync strongly connected component. I do not know whether this is what you wanted to make, but we would like to make a statement of this form, that is if it satisfies some condition, then V belongs to sync strongly connected component. So let me try to make one guess and you can tell me whether it is correct. So I will say that, okay, anyway that sync vertex must have been reached at a very later point, right? So it must have got a large pre-visit number, right? So I will claim that if it has the highest pre-visit number, then it belongs to a sync strongly connected component. I mean, this is my claim, right? So if V has max pre-visit number, then V belongs to a sync strongly connected component. Good, actually it is not true. I wanted you to make these observations and say that this is not true. This is not true at all, that it has a max pre-visit number, then it belongs to a sync strongly connected component, right? So this statement is not true. So I am just trying to make some kind of a statement so that you know what are the kind of statements we want to make. Maybe they are not all true. right? So you are good. This is not in fact a correct statement. Okay, so now I will just try to make a high level comment on your statement. You are still saying a statement of the above type. If x2 is a strongly connected component, then something happens, right? But that statement will not help us because nobody has given us the strongly connected component. The statement, but this strongly connected component is not known. I mean, you can say some statements about, okay, take a vertex, ask does it have pre-visit number and post-visit number larger than something, or so on, but of all vertices, but other than that these components are not given to you. So you cannot say that if it will have what, I mean, yeah, the statements may be true, but those don't help us find a vertex belonging to a strongly connected component. That is what if we are lucky, yes, this will happen, but that is, we want to deterministically be lucky, right? Or I mean, we want to have a deterministic strategy that we are going to always find it. Okay, so actually this is not, this cannot be very easily found out in terms of just pre-visit numbers and post-visit numbers. But what one can say is about when can a vertex belong to a source strongly connected component, and we will prove that, right? So now let us see that if you have a component which is a source strongly connected component, what does it mean? It doesn't have any incoming edges, right? So now if you have two components, let's call them x and x prime, and yeah, and suppose, okay, so I'll just erase this x. So suppose you have an edge from x to x prime, which can happen when x is a source strongly connected component, right? And then what we can claim is that the highest post number highest post number meaning the vertex that gets the highest post number in this strongly connected component is larger than the highest post number in x prime. So I will say what is max of post of v, where v belongs to x prime, right? You understand this term. And then max of post of v, where v belongs to x, right? These are the two terms. So my claim is that this number, let's call it px and px prime. I want to claim that px is greater than px prime, right? Px is a number which is obtained by the post visit number of some vertex inside this component, and px prime is the post visit number of some vertex inside this component, right? And they are valid post visit numbers, therefore they lie between 1 and 2n, right? Okay, again the statement is again of the flip type that we have, but we will make use of this statement to get the correct kind of statement that we want. Okay, so now first let's ask, is this true? So what can happen during the DFS exploration? Maybe we chose some vertex inside this component, right? In which case we have given pre-visit and post-visit numbers to all the vertices in x prime, and therefore clearly if we chose x vertices in x later, then the max post-visit number is going to be larger here than this, right? What can you say in the other case? That is, we chose vertices inside this component, some vertex inside this component for exploration. You must have traversed this edge and therefore explored all the vertices in the x prime, given them post visit numbers, and then come back to some vertex in x and given it a post visit number, right? So because of this, the witness edge which is going from x to x prime, therefore you must have given a larger post visit number to some vertex inside this component. Is this clear? So irrespective of whether we choose a vertex inside x or x prime to be selected for the DFS traversal first, we have this property that the max post visit number given to a vertex in x is larger than the max post visit number given to a vertex in x prime. Everybody okay with this? Yeah, okay. So now, what is a vertex? How can we now use this to say what vertex belongs to a source strongly connected component? So need not be that x is a source strongly connected, or maybe there is another component y which has an edge to x. But then you know that y will have a max post visit number which is larger than x, the max post visit number of x, which will in turn be larger than the max post visit number of x prime. and you can keep going this, but you already know that there must be a source strongly connected component, in fact multiple source strongly connected components. So now what can you do? So now we simply look at the post visit numbers of all the vertices. We pick up the vertex which has the max post visit number. What is, we don't know the component. We don't know the component, we just know that that vertex belongs to a source strongly connected component. But that was not what was our interest, right? So we know how to identify a vertex belonging to a source strongly connected component. So a vertex with max post visit number belongs to a source, I'll write just SCC, right? It belongs to a source strongly connected component. But we have actually got exactly what, I mean, we have got a flipped answer. We wanted something which belongs to a sink strongly connected component, but we got something that belongs to a source strongly connected component. Now, any ideas about how to make use of this fact? Okay. It is a source strongly connected component.
So the complement graph, the source will be sink.
Complement or reverse? Reverse, you are saying. You initially said reverse.
Reverse always. The new graph, source will be the sink in the good.
Very good. So now what he is suggesting is that you reverse the graph, and the reversed graph has this property that one, the strongly connected components, the way we have defined, have remained unchanged, right? If Y was a strongly connected component in G, Y continues to be a strongly connected component in GR, which is the reverse of the graph, because we had said that there is a path from A to B as well as from B to A. So the A to B path is going to get reversed, and the B to A path is also going to get reversed, and therefore the strongly connected components of G and GR are the same. This is a very useful and very important observation that we have made. And now what he is also saying is that if we have a vertex if we have a component which was labeled as a source strongly connected component in GR, that is actually a sink strongly connected component in G, and that makes the deal, right? Now we know that a vertex is with a max post visit number is belonging to a source strongly connected component. So now what algorithm does all of this suggest? What kind of algorithm can we come up with using all these observations that we have made? So remember our task again. We want to find strongly connected components of G, that is label vertices of G's with a component number such that they belong to the same strongly connected component. For this we said that okay, I will actually, if I am able to find a vertex belonging to a sink strongly connected component, I will start my exploration there and actually label all the vertices, delete all those vertices, and then continue this exploration. But now we have made some observations about the reverse graph. So what should we do in terms of the reverse graph? Okay, do the DFS of the reverse graph. Very good. Very good. Excellent. So let us write down your algorithm. And in fact, this algorithm is attributed to Tarjan, and he has given this very elegant algorithm. So what we do is, this is called as strongly connected components of G. So we find GR. So GR is the reversed graph. So everybody understands what is the reverse graph, right? If AB is an edge in the graph, original graph, in GR BA is an edge, and so on for every edge. So this you compute the reverse graph, compute DFS of GR, and let pre-visit and post-visit be the numbers given to all vertices. Now we want the vertex with the maximum post visit number, right? Because we said that that vertex is going to belong to a source strongly connected component of the graph GR. So we will say that we will simply sort this sort vertices according to post of V. Remember that this post of V is the post visit number given on the DFS of GR, not on the DFS of G, and we can sort these numbers, that is we sort them on post visit of V, and then select, I should write repeatedly select the max post visit number vertex and perform. Actually we now can simply perform the DFS on the directed graph G, but the pre-visit number giving is not important to us. We can actually do what we did early in the class, that is the connected component number should simply be incremented, because that is all we want. The pre-visit numbers and post-visit numbers of G itself are not going to be used for the connected component computation of the graph G. So you, after this you certainly perform a directed DFS traversal, but when you invoke the pre-visit of V, you are going to simply say that increment the connected component number, right? So I will not write that here, but perform DFS on G starting at V and keep doing this. That is, once you have explored all the vertices reachable from V, you delete them from the graph and keep doing this, right? So you already have sorted vertices. Some of the vertices you may have lost because some of the vertices have been marked as no longer required, right? So when I say delete, you don't have to physically go and delete vertices from the graph. You can say that those vertices have been already given a component number here. So whenever you repeatedly select a max post visit number, if it has already been given a component number, you don't have to again select that vertex, right? So you skip those vertices which have been given a component number, choose the one which has the next highest max post visit number. In the remaining graph, it is going to belong to a source strongly connected component of GR, that is, it is going to belong to a sink strongly connected component of G, right? And therefore, all of it that we are doing, so now let us, so does everybody agree that we actually computed this, we have first chosen one sink strongly connected component, labeled all the vertices as with the component number, deleted virtually the vertices which have been given component numbers by simply saying that when I do this repeatedly select, if a vertex has been given component number, I will ignore that and choose an unnumbered vertex which has not been given a component number and continue doing this, right? And then by the way we have defined the sink strongly connected component, we are only going to explore vertices in that component and no more, and therefore we will explore all of that component, give it a component number and repeatedly continue doing this. This exploration is always going to compute the strongly connected components correctly, right? So let us try to ask what is the time involved in doing all of this in terms of the running time, right? So how long does it take to compute the reversed graph of any graph? N squared. Does it require n squared if it has m edges, where m could be smaller than n squared? But you need not use an adjacency matrix, right? We'll always use an adjacency list representation, m plus n. So it is linear in the size of the graph, right? Every time you see an edge, you insert a reverse edge in your graph, and there are m edges that you will traverse. You will get a linear time algorithm to find the reverse of the graph. That is, you simply add edges, the reverse edge into the other graph, we call it GR. Now DFS, we have already seen it takes linear time. So DFS of GR will also take linear time. What about sort vertices? How many vertices are there? There are n vertices. We sort them. How long does it take? N log n time. Can we do better? My claim is that you can actually do this step in order n time. And you have to note that these numbers are not arbitrary. These numbers are coming from a very strict range which is from 1 to 2n. Right? If you have n numbers which are arbitrary and you are doing any comparison based sort, then you will require theta of n log n time. But these numbers are not something which are arbitrary numbers. These are numbers which are in the range 1 to 2n, and this you should make use of this fact to show that in fact you can sort these numbers in time which is only order n. Right? So this is a very small exercise, very interesting if you haven't thought about it. So just think about it. If you don't get it, please ask me after the class. And then repeatedly select the max post visit vertex V. This again is just by maintaining that in the sorted order, and perform DFS. This DFS is not on the whole graph, because you are now saying that DFS on G has been broken into smaller parts. So in fact this whole thing is going to take order m plus n time, right? It's not going to be some k times m plus n, because you can think of this DFS itself being split into several parts, where it does a DFS of a smaller component followed by a DFS of a smaller component. Again, every edge gets visited at most twice in the whole procedure, and therefore you can say that this loop is going to run in order m plus n time. Therefore the whole algorithm, except this step that which we have not argued is order n time, the whole algorithm to compute the strongly connected components is a linear time algorithm, which makes clever use of the reverse of the graph and the pre-visit and the post-visit numbers that we have found out, right? And this is one of the very celebrated algorithms, and also very clever. And again, pre-visit and post-visit numbers have been exploited at several places in undirected as well as directed graphs to answer queries in efficient time. So I think I'll stop here.